Last week, we looked at the properties of tensors. And I will run through some of the issues. Somebody complained about slide 55. I will go through that. And I will rush through here. And if you have difficulties with any of the slides, please go to the chat room and say so. And I will first of all, before I start, I will first of all give 2-3 minutes for possibility of any question on what we did last week, because it is important we understand the properties of tensors before we do the final property, which is the eigenvalues and the eigenvalue question, which we are going to answer. You need to understand the other things. If you understand the other things, it will be a piece of cake. So I will spend 2 minutes in the chat room now, just in case there are people who have questions. If your question is on slide 55, I'm going to take that. But if there's any slide that we went through or we didn't go through that you want us to spend some time on, let me know, so that before I bring what I have prepared for today, I went through the last week's class and I found that it was loaded, really, really loaded. And it may be the most important things you are learning. Most of the things you were learning before were background. I am sure by the time we got to last week, there is scarcely anybody in the class that is not learning something new. Most of the time before, I was just teaching you vector analysis and teaching them in an advanced way, but it's still vector analysis. But the last time when we are now discussing the properties of tensors, that is our first flight into the real issue. So once we get to the calculus of tensors, this term is finished. From then on, if we were to have the next class, it will be in kinematics. And then there we are now fully in continuum mechanics, because you got the background then to learn kinematics. When you finish kinematics, then we go full into kinetics. But right now, it is the properties of tensors. And like I said, I'm going to go to the chat room so that I can see if there are questions. And then from last week, and then we can take a look. What's the specific question about coordinate transformation? What is the specific question? Okay. So since we didn't have any questions, I will just answer the only question I remember that came from last week. So I'm not going to go through the notes as I wanted to. So I will just go to slide 50 and move to slide 55 and see whether I can answer the question that was asked that I did not deal with last week. So let us go and do that. So we discussed the inverse of tensors. We proved that if y is the inverse of t, t is also the inverse of y. That's what we did there, and we proved it. Then we showed that tensors can be written in terms of 9 components, and those components are the basis of those 9 components are the dyads, and there are 9 dyads. And those 9 dyads, even when they look alike, are not the same. We've showed that E1 dyad E2 is not the same thing as E2 dyad E1. And here we showed how if you are given a tensor, then you can find the components. You can find this equation here. There are 9 equations. So if alpha is 1 and beta is 2, or alpha is 1, beta is 1, and so on, all those ones will give you T11, T12, T13, T21, T22, T23, T31, T32, T33, which will give you all the 9 components just by changing the values of alpha and beta. So there are 9, the 9 components can be found like this. And we also talked about the products of tensors, and we saw that the composition is a product. And we already saw a composition here, because this yt and ty are compositions. And when you have ytu, it means that first of all, apply t to u, and then the tensor you get, you apply y to it. So that's the composition. So yt is a product called the composition. And then these are the components basic components of tensors. Let me just do this thing in projection form. Okay, so, and then we were able to see that the chronicle delta that we've been looking at, and they look like ordinary scalars. They are not. They are just the tensor components. They are scalars, but they are components of the identity tensor, as you can see here. And if you apply it, you can see that instead of being EI, it's only EI. That is, for the what this means is that I want to ask you a question. What's the implication of the last equation here? Now that you are not asking me questions, what's the implication of the last equation here? That I is AI diad AI. Go to the chat room and tell me what that means. How many components do we therefore have for the identity tensor? How many components do we therefore have for the identity tensor? What's the implication of that last expression? So from there, because you can see that okay, let me just see what happened to the other components. What kind of tensor is the identity tensor then? What kind of tensor is the identity tensor then? If it has only 3 components, what kind of tensor is it? What kind of tensor has only 3 components? Do you know a particular kind of tensor that has only 3 components? No. A first order tensor has 3 components, but I'm talking of a second order tensor that has only 3 components. Identity tensor is a second order tensor. It has principal invariants. It has 9 components, just that 6 of them vanish. It's not an annihilator. An annihilator, all the components of an annihilator tensor vanishes. All the components. Yes, the conical delta is a scalar, is the component of the identity tensor. Okay, let me give you the answer. An identity tensor is a spherical tensor. A spherical tensor has only diagonal elements. An identity tensor is a spherical tensor. So we looked at that before. So identity tensor is just the first example of a spherical tensor. Sorry, I just turned that off. Okay, can you see, is it clear that an identity, sorry about that interruption. Can you see that an identity tensor is a spherical tensor? Let us go back to the review. Let me see, where do I do that? Okay, hide this one and then go to the review. Where are we now? And from the current slide. So the identity tensor, because it doesn't matter whether you use this. If you use this, the chronicle delta will make sure that every off diagonal element is 0. Here, the chronicle delta is gone, and then you just say E1 plus E2 diad E2 plus E3 diad E3. That's all you have, and that is it. And then we talked about products of tensors. Other products are With vectors, we have defined scalar multiplication, scalar products, vector product, and tensor product. 4 different ways of you can take a product. That is the reason why when you say you are taking a product, you have to say which one of them, because there are more than one. Whereas when it is scalar, there is only one way to take a product, so there's nothing to do. When you move to higher order, the number increases, but luckily we are restricting ourselves to some practical examples. And we looked at composition. We looked at that is putting things in. That is an additive. When we look at composition, there are other products that you can get in tensors. So then we talked about the transpose, and which defines, it is the transposition that defines symmetry. And then we looked at the scalar that can define a vector. We also have tensors that can define a tensor. But please remember one thing you should never forget. When you see these square brackets are the scalar triple product. That is, the first vector dot, the second one cross the third one, or the other way around. You can put the dot here and cross there, or reverse it. But it's a scalar product. So the result when computed is a scalar. That's why we can have fractions and all those ones. You don't have fractions of vectors. It's because whatever is contained inside that bracket is a scalar quantity. So you are adding one scalar to another scalar to another scalar, so you can sum it up and divide by another scalar. So that is why this is the trace. Okay. So it's not because the idea of fraction is not defined for tensors. It is expected you should have read up the notes from last week. Okay. We also provided here what we mean by the determinant of a product. If you have product of two tensors, like a composition A, B, the determinant of that product is the same thing as the determinant of each one of them multiplied by each other. Because remember again, the determinants are scalar quantities. So these types means only one thing, because we are looking at scalars here. And then you now also have the trace of a composition. Okay, and then the scalar product of two tensors. So when you have the trace of a composition, if you take the transpose of one before the other one, then the trace of the composition is called the scalar product. So here is where we did the proof, and from that point on, we were able to do the inner product of tensors there. And we were able to see that getting the formula we had before for the component evaluation is simply the same thing as the scalar product of the tensor with the base. That is what gives us the component. And then we looked at several other things here, vector space, the decomposing tensors. We saw that we can decompose tensors either additively or multiplicatively. We have seen two examples of additive decomposition. Is it two or three? We looked at breaking them into 9 dyads. That is one, which is similar to what you do for vectors. We can do it in skew and symmetric forms. We can do it in spherical and deviatoric forms. And then there's a fourth one, which is a dyad breakdown, skew and symmetric, spherical and deviatoric, and then there is the spectral decomposition. We will get to the spectral form in today's lecture if we go that far. But there is also a multiplicative decomposition. It is called polar decomposition. This becomes very important when you get to kinematics. And it is so important because from there, if you have an expansion, you can break it into one that changes shape and the other one that doesn't change shape. So you can have stretch and rotation, and it's a product of the two that gives you the full when there is a distortion or change of shape. It is a combination of one that changes the way the shape looks and the other one that just rotates the shape. We'll see that later on. So that's what we argued here. The first form which is the weighted form, is looking like the way we did vectors. It's just as instead of containing 3 terms, it contains 9 terms. And then we saw that if you do trace of dyads, you can, if you do a trace of 2 dyads, all you need to do is to change the dyad product there to dot product, and that's it. So today the trace of a dyad is just changing the dyad symbol there to dot product, and this is the proof here. If you take the trace, if you want to take the trace of a dyad, all you need to do is to just change this dyad to dot, and that is the beautiful thing. That's why when you reduce a tensor to this dyad form, taking its trace becomes a piece of cake. So, and then from there we can move into some of the other ways of decomposing tensors, the spherical and deviatoric parts, and then we showed that skew and symmetric parts also. This is another way, skew and symmetric part. Then what else did we do? Now we went to the transformation of line elements. So if you transform a line element with a tensor, then we want to know what happens to the area that those, if there are 2 line elements that they can form a parallelepiped. If you transform the 2 line elements with a tensor, what happens to the area? That looks like a rhetorical question, but it is not a rhetorical question. It's a very deep question, and it is what leads us to defining the cofactor. Look at this one. If you have vector here and vector here, and you use T to transform this, you use T to transform this, then what happens to the area? How does the area here relate to the area here? And we have seen that the area here relates to the area here by the cofactor. The new area is simply the same thing as the old area operated on by the cofactor. That is why the cofactor has a very, very significant, physical interpretation. And let me remind you something you learned in secondary school. You remember in secondary school when you are doing heat, and you know that heat changes the size of an object. If it is linear, you talk of linear coefficient of linear expansion. Then when it is area, you talk of coefficient superficial, that is coefficient of surface expansion, which is different from the coefficient of linear expansion. And then if it is the volume, you talk of coefficient of volume expansion. So you are not only interested in the expansion of lines, you are interested in the expansion of areas, and you are interested in the expansion of volumes. What we have said here is this: if you know how the lengths expand, you can use the cofactor to know how the areas expand. If you know how the lengths expand, you can use the determinant to know how the volumes expand. So once you know one, you can get the other by the same tensor. So if a tensor expands length, or either expands or contracts length, then the cofactor expands or contracts the area. The determinant expands or contracts the volume. So you don't need to do anything again. You don't need to know anything more than the tensor that affected the length. You can get from it the tensor that affected the area by taking its cofactor, and the tensor that affected the volume by taking its determinant. These are the physical meanings of those mathematics things you are playing with. So here we are not joking. This is real practical computation, and something that has effect on design and actually how you build the built environment. So the superficial expansion is coming from the cofactor, whereas the volume expansion, which relates the original volume, which relates the final volume to the original volume, is determined by the determinant. How determinant is by how much has the volume changed. The cofactor, by how much has the area changed. So the tensor itself is very important, but equally important about a tensor is its cofactor. If you are going to do anything with area, you must know the cofactor. So we cannot just gloss over and run away from the cofactor. That's why we spend time to look at the cofactor. We are going to revisit it once more. Here, we are trying to say, okay, if you have a tensor, can you get the coefficients of the tensor in terms of the cofactor in terms of the coefficient of the original tensor? Yes. And that is what we did here. It looked initially a little bit laborious, but I was able to show you there is no step there that is not simple. and then from there we can relate the trace of the cofactor. We can relate the trace of the cofactor to the square of the trace and the trace of the square. The first term here is the square of the trace, and the second term is the trace of the square. The square of a tensor is when you do a composition of the tensor with itself. That is the square. Just like the square of a scalar and of a vector is when you take the dot product of the vector with itself. So if I say v dot v, it's the same thing as v squared, because it's a scalar and it's the squaring of the magnitude of the vector. Similarly, for a tensor, when you take the composition with itself, then you have a square of the tensor. So here we just arrive at the standard definition of the cofactor, which is that it is the transpose of the inverse multiplied by the determinant. That's why you can use the cofactor to compose the inverse, because if you take determinant and use it to define the cofactor and you take its transpose, you've gotten the inverse of the thing. But you don't even need to go that route. You can just calculate the cofactor straight away, as we have demonstrated in this derivation here. So what next? We now ended with orthogonal tensors, and that's where somebody raised a question. We said an orthogonal tensor is a tensor that does not change magnitude. And how do you know it doesn't change magnitude? We will see that if it doesn't change magnitude, that is, if we transform A and we transform B and we get their dot product, the dot product before transformation is the same thing as the dot product after transformation. In particular, if you are transforming the vector and you are dotting it with itself, it doesn't matter whether you do it before transformation and you do it after transformation, the answer is the same. That means that the magnitude of the tensor in the beginning does not change after transformation. So that is what defines an orthogonal tensor. And then we said that if that is the case, let this small q be QA. If we have QA dot QB, this is where somebody raised the question last week, and it's until I got back home that I was able to really see what was confusing him. We first of all said that QA dot QB is same thing as A dot B. So if we made QA to be this small q, this expression is the same. But this equation is because the dot product is commutative. So A dot B is the same thing as B dot A. So if we do that, from here to here, we recall the definition of transpose. So if Q dot QB is the same thing as B dot Q transpose Q, because that is the definition of transpose. But here we remember that we said Q is equal to BQA. So if we change it, we now have that B dot Q transpose QA is equal to B dot A. But we know that B dot A and B dot A is the same thing as QA dot QB. So if that is the case, this B dot A, this B dot A, this B dot A. So if you look at these two expressions, if B dot QTQA is the same as B dot A, that shows that this thing must be the identity, because that's the only way these two things can be equal. They can only be equal if this is the identity that didn't change A. Otherwise, they cannot be the same. So we conclude that QTQ is I. And this is a condition that is necessary and sufficient for a tensor to be orthogonal. The condition is that the tensor must be invertible and its inverse is equal to its transpose. If a tensor is invertible and its inverse is its transpose, that tensor is definitely an orthogonal tensor. So every orthogonal tensor possesses an inverse, and this inverse is simply the transpose. But remember, the original definition of transpose is that it does not change magnitude. Okay, so that is what we were saying here, and that's what. So I have explained. Let me see whether the person who asked a question last week is still there, and he still has a question. Let me go to the chat room to be sure that his question has been answered. Chat room now. So if we're in the chat room, okay, the question has been answered. Okay, is that the question for last week? Are you the person who asked the question from Ebonua? Are you the person that asked the question concerning slide 55? Okay, good. So I can move on now. So please don't notice that if you have any difficulty, put it in the, but your difficulty, let it be specific, because otherwise you are wasting the time of the class. It's not that I can't talk to you. I can teach the whole thing all over again, but I have to consider the rest of the people in the class. That's all. So let's go on. So we now came here to look at the determinant of an orthogonal tensor. So the determinant of orthogonal tensor is either 1 or -1. So that is, we proved that here. So it's either +1 or -1. When the determinant is +1, we call that tensor, that tensor is not just orthogonal, we call it proper orthogonal. What happens when the determinant is -1? We don't call it improper orthogonal. We just say it's orthogonal. That's the practice. So it's not. So there are two types of orthogonal tensor. There is the one that is proper orthogonal, and then the other one is ordinarily orthogonal. So we just say this tensor is orthogonal. That means that its determinant can be plus or -1. But when you say it is proper orthogonal, you are saying that the determinant is +1. And that is important because when you are doing transformations, you know that proper orthogonals gives real transformation, and the other orthogonal may give virtual transformations that do not really exist in fact. And like I said, if somebody is going to send a drone to kill you, just hope that the mathematics of computation of the location of the drone was using an improper orthogonal, an orthogonal that is not proper orthogonal. So it's going to fire all the missiles at your image, and you'll still be alive. But if it is the proper orthogonal, you are good. You are good. You should have written your will before that day, so that you will not, so that people that survive you will not be wondering what to do with your property. Okay, so that's it. So here we also said that a proper orthogonal tensor is self-cofactor. For any pair of vectors, we show that QU cross V is the same thing as QU cross QV. Ordinarily, this should be QC, like here. This is the correct expression for any tensor. For any tensor, this is true. But what we are saying is that because we are dealing with orthogonal tensor, there's no difference between QC and Q. So if we start like this, we remember that QC is the cofactor of Q, which is, this is the formula for cofactor. If it is a proper orthogonal, that is a rotation, for instance, if it's a proper orthogonal, the determinant is 1 plus 1. And now Q to power minus T is written as inverse of Q transpose. But the inverse of Q is the same thing as Q transpose. So it is the transpose of a transpose. The transpose of a transpose obviously gives the original tensor. So with this one being 1 and with this one being the original tensor, we can see that the cofactor of a proper orthogonal tensor is the same as itself. Now, class, I want to tell you something at this point. I want to tell you that if we look at it in another way, we have just been wasting the last 5 minutes. Because everything we have said here, if you look at it from a physical point of view, it should be obvious. So I want to ask, is it obvious to you? I want to find out if it is obvious to you, and I will spend 5 minutes to show that it ought to have been obvious to you. What we have derived just now ought to be obvious to you. If it is not obvious to you, you are still lacking in some physical intuition that you should have got. Is it obvious? Is it obvious that the cofactor of an orthogonal, of a proper orthogonal, Do you think we should have been able to see that without all the mathematics? That's my question. Should we be able to know that the cofactor of a proper orthogonal should be itself? Is there anybody in class for whom that is obvious, which should make the entire mathematics we did in the last 5 minutes unnecessary? That you should be able to see it. I want an answer. If it is not obvious, say no. Because so that when I go and now make sure, because at the end of my explanation, I will ask the question again. Okay, Caleb says it's not obvious. Omotola says it's not obvious. So is there anybody for whom it is obvious? I want to say that it ought to be so obvious that we shouldn't have done any math. And should be obvious from just a physical reasoning. Okay, so since everybody is answering no, we will go back to the slides. And I am betting with you that by the time I finish, everybody that said no here is going to say yes. Okay, good. That's enough. Let us go back. Let's go back now to the slides. Because when I was reviewing it, I just said, why am I doing all this math? It should be obvious to everybody. So what we are going to do is that, let's see here. I'm going to take the slides now. I'm going to project and I will go back. We are in slide 57. So let us go back to slide 30 something. Oh, is it 40 something? Okay, let's go back to 40. We are going back to slide 45. We are back here. Okay. You see on the right-hand side here, vectors u and v. And below it, you have vectors tu and tv. And we are looking at the area that there are parallelograms create. And that area is the cofactor operating on the previous area. Now, if we are dealing with a proper orthogonal, what we are saying is that TC should be, if it is Q, it should just be Q. There should be no difference between Q and QC. There should be no difference. Why should there be a difference? Look at it. If all that happened in the transformation is just a rotation, if it's only a rotation, so if TU is just a rotation of U and TV is just a rotation of V that did not change should the area change? If you have two vectors and you transform them only by rotation, the same rotation for both of them, should their areas change? So let me just ask that. So answer me, should their areas change? Please, chat room. Should their areas change? No, the areas should not change. So that means that whatever you use to transform the same transformation that didn't change the length should also not change the area. If it can't change length, it cannot change the area. So it must be the same tensor that transformed the original that is also transforming the area in the case of pure rotation. So when what happened is just a matter of rotation, there should be no need to change anything. So that, because remember the determinant of the cofactor is the same thing as the determinant of the original. Same thing in there's no difference when it is a rotation. There's no difference between the cofactor and the tensor. It should be obvious because there is no change in the area. Now I want to now put another difficult question that is now difficult. Why didn't we just say, looking at the fact that what is it? Let me first of all start. What is the direction of U cross V? What is the direction of U cross V? Do you agree with me that the direction of U cross V should be the perpendicular to this surface? Now, if all you did is a rotation, why don't we just say that TU cross TV should just be U cross V? Because if you rotate and the perpendicular does not change, so there should be no Q multiplying U cross V. It should just be U cross V. TU cross TV. Why is it not just U cross V? Since the cross product is in the perpendicular direction. If you rotate, if I rotate something in the perpendicular, you know that is nothing happens to it. Why should it still have to be Q U cross V? That is the last puzzle. Why is the Q still necessary? We have seen now that the area cannot change, but is the Q still necessary in this equation here? Let me go back to what we are looking at. This is the equation we are talking about. In this equation, in this last equation, since U cross V which is U cross V is in the direction perpendicular to U and V, why don't we just say QU cross QV should simply be U cross V? Why? We already see why it should not be. There's no difference between the cofactor and the tensor itself. It should be obvious. But why is Q still here? And that is the final insight issue that I want you to see. That provides a very deep insight. Why is this Q still here? Why can't we just say QU cross QV is simply U cross V? Why must we retain Q here? Now, but if Caleb, you are saying to indicate the angle of rotation, but look, remember, area is the area times the perpendicular in the perpendicular distance. If the perpendicular distance, the perpendicular vector, if you rotate, the area does not change. Does the perpendicular direction change if you rotate the area? Does the perpendicular direction change if you rotate the area? It does not. I shall. You agree with you. It does. It appears. Apparently, it does not. I say apparently. Yes, I want you all to answer the question, and then I will tell you why Q is there. Alas, there is something you are missing. There is some trick you are missing. It should change. Let me tell you why it changes. Let me now tell you why it changes. And that is the clincher. It initially appears that Q is not necessary, but Q is absolutely necessary. And let me now show you why Q is necessary in the expression. So project from the current slide. Okay. Now, what I said earlier would be true if the rotation was plane rotation. If the rotation occurred on the plane, then this becomes identity. It doesn't, because the value of Q, or for a plane rotation, for a plane rotation, the value on the area does not differ from that identity, because since the area is not changed, so the magnitude doesn't change and the direction didn't change. But what if the rotation was not on the plane? For an abstract absolute rotation that does not have to happen on the plane, Q is what you really need to still operate on, because the vector area will change. It will not change in value, it will not change in magnitude, but it will change in direction. And the change in direction is caused by that same rotation. That's the trick here. If you are discussing only plane rotation, that previous argument would have been valid. But because we are not limiting ourselves to plane rotation, we just said rotation. We did not say plane rotation. The rotation can happen in any way. It can happen in any axis. In fact, it can even be one vector you are rotating about another vector. If that is what you are doing, the area would have changed in direction too. And we are saying that the direction of change in the area is governed by that same rotation. That is what this equation is saying. So this equation is more general than what we will arrive at if we are only considering plane rotation. Thank you for that level of insight. So we can move on now. So what do we have left? We are now talking of one eigenvalue of a proper orthogonal is +1, but we have not really introduced what eigenvalues are. So we will come back to this slide 58 later on. So let us leave it at let us leave it there and go on a 10 minutes break. And after that, we will come to today's topic, which is the eigenvalue problem. I want you to relax, and 10, that is 11:05. We are going to start the second part of the lecture, and I'm going to introduce the eigenvalue problem. And you will get the slides at the end of today's class. I have not sent the slides to you yet, but I already have the slides done. So the eigenvalue problem is the next thing. So I will stop the microphone now, but I will still leave. So you can still, before I start the lecture again, I will take a look at the chat room and see if there are questions waiting for me there. So if you still have questions, please put them in the chat room. I will take a look at it, but we will meet again. That is 11:05.